Okay, so welcome again. And you can see on the screen, we have got a very interesting circuit. It's called as bridge amplifier that can be used to process the signal variations from the sensor. We are going to explain that in a moment. So you see that it is a two-stage instrumentation amplifier. We've got two operational amplifiers configured in a negative, using a negative feedback. We configure both of them in an inverting mode. So input is coming to an inverting mode and output is fed back to the input, the negative pin of the amplifier. Here also input is coming to the negative pin and output is coming back to the negative pin. So so this is an IA instrumentation amplifier, and here we've got the bridge, commonly known as Weston bridge, with the four resistors. This is actually a resistor with a 0 ohm, so you can replace it with a short as well. This is just to set the common mode voltage of overall circuit. That's why this extra resistor. One of the four resistor, that is the R12 here, is modeling the effect of a sensor. For example, a strain gauge that can sense changes in an external pressure or external force, and it experiences a strain, change in strain, and its readout therefore is a change in resistance. So when there is a change in resistance of the strain gauge due to external applied pressure or force, the bridge, which is originally balanced with this voltage at this node and voltage at this node to be equal or approximately equal. Now, with the variation in the change in resistance of R12, there'll be a big difference between the two voltages at this node and at this node. Those voltage difference, or those voltages V1, let's say, is coming to the positive pin of U1A part, and this voltage, let's say V2, is coming to the positive pin of U1B part. And V1 and V2, when there is no change in resistance, are of equal values, so their difference is 0. However, when there is a changes in the resistance, you got some difference between V1 and V2, which are applied to the positive pins here. And this amplifier is then a difference amplifier. One of the input is to the negative pin and second input V1 is to the positive pin. Here also the output of the first stage is the input to the negative pin, and to the positive pin, the input is V2. So that's the basic principle of operation. Here you see that there is a negative feedback, and from here also there is this negative feedback. So here you got the two negative feedback right over here. Now, there is the reference voltage set to be of 2.5 volts to the first amplifier. That's the reference voltage. And here Vx is the voltage of set to be 2.5 volt, which is coming right over here. So if you want to highlight the nets, you can just go and select this option, highlight net. And then if you click here, then all the nets which have the same signal will be highlighted if you right. So that's the purpose. Now we will understand the basic manufacturing spice model of the part. Okay, so we'll see that in a moment, how we will use the spice model. So you can see that we have got this spice model from the Google. What I did is the IC number is TL072. I typed this number in the Google and said, okay, give me a spice model for TL072. So with that, I got to the manufacturer website, and there I found the spice model, which I then saved into my download folder, for example, right over here. So it was this folder in the zip file, and then I got to open it. So let me show you. So when I unzipped it, I got the first file TL072. So if I double click here, I see that I have got this model right over here, spice model. And in our previous model, we have explained you so many times how to read this spice model file, the what is sub-circuit, the pin sequence. You see that the first pin of this IC is non-inverting input, second is inverting input, third is positive power supply, fourth is negative power supply, and five is the output. And then I open one blank text file, and then because I need to use the two operational amplifier as shown in my schematic, I need to use two parts, okay, U1A and U1B. So I need to call this spice model twice in my circuit simulation. So to do that, what I explained is this one. I need to I got this code from the ngSpice website, which says it is a dual Opamp ngSpice model. File name is .lib. It has an extension of .lib. The name of the file is TL072-dual. And then I'm calling this subcircuit with this syntax .subcircuit TL072C. Then the first unit, the out pin, in minus, in plus, then VCC minus, that is the VEE also, or negative power supply. Then second unit, in plus, in minus, and out. And then I have got VCC plus, that is a positive power supply. And then I have used this dot include TL072, which is actually the file I showed just below, this file right here. And then X uh, is basically calling, I'm instantiation this blocks XU1A, the first pin, positive pin, negative pin, then positive supply, negative supply, and the out. Okay, this sequence is what we saw right here in this file. First pin is non-inverting, that is positive, then negative pin, then positive power supply, negative power supply, and the output. So similarly, you have to make sure that in this file you have this sequence and then the model name. So you call it two times, because for the first part and the second part, and that dot ends. With that said, what you can do, come back to the schematic right over here. Let me take you to the, well, don't save it. Let me take you to the schematic right over here. Okay. And so how I actually got this part is simple. We have explained that in the previous. Click here in the library, and this box will open. Then type TL072 or just like that. So I have recently used it, that's why it is showing right here. I have already placed that, and that's why it is showing right here. Otherwise, when you will type it first time, you will have such options. So you can use this single low noise JFET input or TL072, what we want. So it has got three units. That's the unit A. Unit B, look at how the pin sequence are changing. For unit A, pin sequence are 3, 2, 1. Unit B, 5, 6, 7, and unit C is like that. And this is power input and fourth. Okay, so I have placed all of them here. So this is unit 1, unit 2, and this is my power supply pins. Once that is done, I can double click here, and you see that all the information we have explained this. So you are first time, if you are here first time, you are encouraged to refer back all of our previous model. There we have explained these details about how to call the spice model, and all that. So many things, useful tips and tricks have been explained. So I will click simulation model. Then you see that this field was blank. So I clicked here, and then I went to my download folder and this unzipped file in which I had this first file. And I forgot to tell you that this the text file, the empty text file, when I put this code in this empty text file, I saved it with the name as shown right over here in the same folder where this file is present. These two files must be in the same folder. Okay, so what I'm going to do is here I have to call the .lib file. So .lib file is this one. So I click and I opened it. So I got the path and then I clicked here and then I select this. That's it. Once that is done, I click OK. But before that, click simulation model again. See the pin assignment. The symbol is what you see on the schematic editor of KiCad, and the model pin is what you see in the model file. They must be properly matched. So pin number 1 in symbol is the pin number out in the model. Second pin is the negative pin. So it is the in the model pin, the pin number 2 is this one, negative one. That is the positive pin here. This is the positive pin here. This is the negative power supply. This should be negative power supply. So you don't have to really match this. Once you load that lib file, you will see that there'll be a perfect map with this one. But if you do some mistake, it won't be the match. You can just click here, So just note the pins 1, 2, 3 and see what pin is what. Here also what pin is what. Here also what pin is what. And just compare that with the model pins. And if there is a proper match, your simulation results will be correct. Otherwise, it will be difficult to understand or there'll be a wrong result. Here are the power supply plus minus 15 for the Opamp I have used. Once that is done, I will go to simulator and I have run this DC sweep analysis. I will show you. You click here, edit analysis tab, and in the edit analysis type, what I sweep is this, the R, resistance R. Which resistance? R12. Why R12? Because that's my sensor. That's my sensor, and I'm varying it from the starting value of 100 to the final value of 200 with the increment of 1. So I click here. So let me show you where is my register here. Here is my register R12. Nominal value is 120 because other register values have been 120. In fact, the nominal value of the resistance, which is a strain gauge sensor, is to be measured first. If it is 120 as shown, for example, you have to create a Western bridge by choosing the values of other 3 register to be the same so that the bridge is balanced. And now this resistance we are sweeping. So come back here, come back and click simulation. Now you see I have got this simulation results where I have plotted the final output VO2. Where is my VO2? Come here. Here is the VO2. Okay, that is the final output. Once I do that, I see when my resistance is like about 99.7, so my output is minus 6.9, something like that, and thereafter it linearly increases with the increment on the resistance value on the x-axis. Okay, but just let me fit on the screen, and it goes up to 14 volt maybe. Let me check. Yeah, 13.20 is linear, and thereafter the output saturates. So here, from here to here is my linear range. Okay, now what you can do is play around with different parameters, change maybe the reference voltage, change maybe the supply voltages of the PAM, and just see what's the difference are. For example, change this voltage, change this voltage reference, change the supply voltages, and just go on doing that. So let's say reference voltage is now 4 volt. Okay, and once that is done, save, go to simulator and click here. Look at this, there is some change from the original. Now it is minus 5.4, and then it is like something like that. Okay, go back again and keep the reference maybe Z 2.5 same before as before, but now just click here, go to settings, and once that is open, instead of 100, let's say you want to have a large variation, see how far it goes. So let's say 50 to 250. Once that is done, simulate. Now look at this. negative saturation of the sub volt Opamp and the positive saturation, and this is your linear range of the resistance. So just keep playing, keep doing it, and you will see that you got to design, you have designed a real world bridge amplifier for the strain gauge sensing application, or for that matter, any other sensor um, which provides outputs in changes in its resistance due to some external physical quantity exerted on it. You can process that change in resistance and and convert it to equivalent voltage. That's what we have done it. Okay, so with that said, hope you like this. If you did so, share this with others for wider reach. Then stay tuned for more engaging content like this, and wish you all happy learning.